Welcome again, chemistry students. This video, we're going to discuss some topics in measurement that you will be needing for your General Chemistry 1. So these topics will include physical quantities, accuracy and precision, significant figures, scientific notation, measurement of density, and conversion. So to start with, let's define measurement. What is measurement? Measurement is obtaining any numerical values or data from experiments. So this is done by using some measuring devices such as ruler in measuring small lengths, a meter stick. We also have weighing scales to determine mass, and many others. Some examples of measurements are 5 kilogram. So we have magnitudes when we are doing measurement. We assign value and we choose a unit. Length, we have 100 centimeter, and for time we have 500 seconds. So what are we measuring? We are measuring fundamental quantities, which are divided into two groups. We have the fundamental and the derived quantities. For fundamental, we have 7 fundamental quantities. These are the following. One is mass. Mass may be expressed in many different units, but the fundamental of all this is kilogram. Another is length. The fundamental unit is mass. Time, we have second. Temperature may be expressed in 3 scales. We have degrees Celsius, degrees Fahrenheit, and Kelvin. But among the 3, the fundamental is Kelvin. Luminous intensity, candela as the fundamental unit. Symbol is CD. Electric current, ampere or A. And amount of substance, mole. For the derived quantities, we have some examples. Volume, density, weight, energy, pressure, mass, work, and many others. Since we only have 7 fundamental quantities, all the rest of the quantities that you will encounter will definitely fall under derived quantities. The units that you see here are based on the International System of Measurement. This is the system of units modified in decimal fashion by a series of prefixes. Let us have some examples of, let me correct that, that's derived quantities. So one is volume. Volume may be determined as the product of length, width, and height. So notice these 3 are 3 similar units. They are 3 lengths. So volume is a combination of 3 fundamental quantities. So that's how we define derived quantities. Derived quantities that are combinations of 2 or more similar or different fundamental quantities. Like in the case of volume, we combine 3 fundamental quantities which are 3 lengths. Another example is density. Density is expressed in gram per cubic centimeter. So for the formula, you will see the equation mass over volume. So mass is a fundamental quantity. Volume is a combination of 3 fundamental quantities. So density is a combination of 4 fundamental quantities. Let's have another velocity. Velocity is meter per second. This is determined as the ratio of distance over time. So distance is length, time is another fundamental. So velocity is a combination of 2 fundamental quantities. And the rest, you will see that they are combinations of fundamental quantities. So they are what we call again derived physical quantities. Let's move on to some common prefixes used in measurement. So we have kilo. Kilo denotes 1,000 times greater than a unit or a preceding unit. In exponent, it's 1 or simply 10 exponent 3. Hecto is 1,000 times greater. Deca is 10 times. Deci is 10 times smaller than a preceding unit. In exponent, exponential form, it's 10 raised to negative 1. Centi means 100 times smaller. Milli is 1,000 times smaller. And micro, 1 million times smaller. Examples. Okay, we have here the equivalent kilogram to gram. So as I said earlier, we have kilo as 1,000 times greater. So in 1 kilogram, we expect 1,000 times gram, 1,000 times gram. Same with the centimeter. Centimeter, meter is greater. Greater by how many times? 100 times. So 100 centimeter equals 1 meter. So in 1 meter, we have 100 centimeters. Or if it's the reverse, 1 meter equals 0.01 centimeter. So you can always have the opposite. So if it's 1 meter, it should be 100 centimeters, or 1 centimeter equals 0.01 meter. So that's it. Another is liter. Liter to milliliter. Milli is 1,000 times greater. So you have the equivalent 1 liter equals 1,000 times of milliliter. So that's how you make use of prefixes in measurement. Let's now move on to the difference between accuracy and precision. Of course, when doing measurement, we aim for accuracy. But when do we say that our measurement is accurate? The term accuracy refers to the closeness of a single measurement to the true value. Precision, on the other hand, refers to the closeness of several measurements, not to the true value, necessarily from the true value, but from the or to the common value. Let's have this as an example. Let's make use of a ruler. Notice here 3 measurements A, B, and C. So we have different measurements of length. We have A, 1.55 inches. B, we have 1.97 inches. C, we have 1.97 inches. So when do we say that the measurement is accurate? We have to compare the individual measurements with the true value. What is the true value? Let's say the true value is 1.9. So which among these 3 measurements is considered or are considered most accurate? So we have here A, 1.55. That is not too close to 1.9 as a true value. B, we have 1.9. Very, very close to the true value. In fact, exactly as the true value. So we can say that measurement B is accurate or most accurate. We have C, 1.97 inches. So this is close, but B, measurement B is still closest to the true value. So among these 3 measurements, we can conclude that measurement B is most accurate, measurement A is least accurate. For the precision of the measurement, we have to determine the common value. To determine the common value, we get the average of the 3 measurements. So getting the average of the 3 measurements, we add 1.55, 1.9, and 1.97 inches and divide the sum by 3. So you will get the average 1.81 inches. And then you compare the closeness of the 3 measurements to the average or common value. The average is what we consider the common value. Are 1.85, 1.9, and 1.87 close to the same value or common value 1.89? Not all, because 1.55 is not too close to 1.81. So we cannot exactly say that the measurements are precise. One of them is most accurate, which is measurement B. But in terms of precision, we cannot say that they are precise because not all of them are close to the common value or the average. To determine the accuracy, you can also check the percent error. The smaller the error in the measurement, the more accurate is your measurement. So percent error is determined as the difference of experimental value and true value divided by the true value times 100. So in the case, for example, of measurement B, to determine the error, experimental value 1.9 minus true value 1.9 divided by true value 1.9. So experimental 1.9 minus 1.9 divided by 1.9 times 100, you will get 0. So that 0 indicates that the measurement is too accurate, very accurate, because it's exactly as the true value. On the other hand, for example, you determine the percent error for measurement C. So experimental value 1.7 minus true value 1.9 divided by 1.9 times 100, you will get less than 5% error. When the error is less than 5%, we can say that the measurement is accurate. So the smaller the percent error, the more accurate is your measurement. Let's now move on to significance of figures. What are significant figures? Significant figures are digits or numbers in a measurement that are known precisely, plus one last digit that is estimated. If we are after accuracy, why do we have the term estimated in the definition of significant figures? Let's take a look again at this ruler. So let's say we are doing some measurements. Let's say we do again measurement A. So as in the previous slide, the first measurement done gave us 1.55 inches. Why is it 1.55 inches? If it is exactly along this line, exactly between 1 and 2, of course the measurement is 1.5. But notice the line does not fall exactly at the line or on the line between 1 and 2. It is between 1.5 and 1.6. Exactly in the middle of 1.5 and 1.6. So we can say that 1 and 5 are accurate, but the third digit 5 is just estimated. So that's what we mean by estimation. The last digit is the best estimate that you can do, but is considered still as significant. Let's take a look at another example. 1.9. Why is it 1.9? Because the measurement is exactly at that mark. 1.9. So the last digit here is 9. So 9 is considered the estimated. 1 is most accurate, is precise. 9 is estimated. But the two values or digits are considered significant. For the third measurement, you will notice the measurement does not fall exactly between 1.9 to 2, but it is closest to 2, but not exactly marking the 2 inches mark. So for the digits, 1 is precise, 9 is also precise, but it exceeded 9, so it may be 6, 7, 8, or 9. So it may be 1.96, 1.97, 1.98, or 1.99. So the third digit is considered estimated, but still considered significant. So that's what we mean by precision and estimated in terms of significant figures. Okay? Yeah, the 7 digit is already estimated. So in terms of significance of digits, we consider the following flow chart. So you will see here the breakdown of digits as non-zero and 0. So to recall the guidelines, guideline 1 states that all non-zero digits in a measurement or in a number are considered significant. For example, we have the number 987,865,231. Since all the digits are non-zero, all the digits are considered significant. So in this measurement, we have 9 significant figures. For the zero digits in measurement, it depends on the position of the zeros. We have three types of zeros in measurement. We have the leading zeros, confined zeros, and trailing zeros. Let's take a look at these examples. So for example number 1, we have 0.00231. How many significant figures? We have 3 significant figures. These zeros are called leading zeros. Zeros to the left of non-zero digits, as well as that zero to the left of the decimal point, are not significant. So in this case, you will only take into account the non-zero digits, because guideline number 1 again states that all non-zero digits are significant. Another example, we have 987,231,000. So we have here another type of zeros. We have confined zeros, zeros in between non-zero digits. These zeros are always significant. So this number will give us a total of 9 significant figures. Confined zeros, zeros between non-zero digits, are always significant. And for the last set, we have trailing zeros. So we have here 987,000. These 3 zeros following 987 digits are what we call trailing zeros, and these zeros are not significant unless you put a bar over the zeros to consider them significant. But in this case, the zeros are trailing and are not significant, and therefore this number has 3 significant figures. What about if you have the last number 0.00231,000? Why is it that there are 6 significant figures? So we have 2 types of zeros here, the leading zeros and the trailing zeros. But as another guideline, zeros to the left of a non-zero and a decimal point are not significant. Zeros to the right of a non-zero and a decimal point are significant. So in this case, you have the first 3 zeros as not significant, and the next 3 zeros to the right of a decimal and the non-zero that are significant. So this gives us a total of 6 significant figures. So those are the guidelines in determining numbers of significant figures in measurement. Okay, can you tell the number of significant figures in this measurement? So in 24 ml, we have 2 non-zero digits. According to guideline number 1, all non-zero digits are significant. Therefore, this measurement has 2 significant figures. Number 2, we have 3001 gram. Zeros are between non-zero digits and therefore significant. So this has 4 significant figures. Number 3, we have 0.0320. The first 2 zeros are not significant. The other 0 to the right of a decimal and a non-zero is significant. Therefore, it has 1, 2, 3 significant figures. 4, we have 560 gram. The 0 is a trailing 0, therefore it is not significant. So this number has only 2 significant figures. And the last one, when the number is expressed in scientific notation or exponential form, you only take a look at the base here. So 6.40 has how many significant figures? 3. The 0 is to the right of a non-zero and a decimal point, and therefore significant. So this has 3 significant figures. You are disregarding the power of 10 when counting for the number of significant figures. Only in the base that you are counting the number of significant figures. Moving on, how do we apply the rules in significant figures in doing calculations? So in addition and subtraction, we follow the same guidelines or the same rules. For example, we are doing this addition, 89.332 plus 1.1. So notice both have decimal places. In the first number, we have 1, 2, 3 decimal places or decimal digits. We have 1 in 1.1. So in expressing the final answer, you get the number of least significant, least decimal place. So you get the one digit after the decimal point as reference for your final answer. So if you get a sum of 90.432, for example, that's the sum of the two here. So you have to round it off in such that you will reduce it with one decimal place by doing the proper rounding off. Since the next digit to 4 is 3, you just drop it and retain 4. So the final answer should be 90.4. In doing subtraction, you follow the same guideline or rule. So we have 2.097 in this case minus 0.12. The initial answer is 1.977. You round that off to 2.097 has 3 decimal digits or places. 0.12 has 2. So you get the smaller digits after the decimal point and express the final answer in the same number of decimal digits. So the final answer should be rounded off to 1.98. Since the digit after the first 7 is 8, you have to add 1 to the last digit remaining. So the final answer should be 1.98. What about in doing multiplication and division? We also follow the same rules or guidelines. So, for example, we multiply 2.8 and 4.5039. The initial answer is 12.61092. In expressing the final answers, you consider the number of significant figures. So you count the number of significant figures in your factors. We have 2.8 here. It has 2 significant figures. 4.5039 has how many significant figures? A total of 5. So compare the number of significant figures. This is 2 versus 5. So you get the least number of significant figures and round off the final answer to 2 significant figures, since the 2 significant figures remaining are 1 and 2, and the next digit to 2 is 6. So you have to add 1 to 2, so that will become 13. So the final answer is 13 with 2 significant figures, the same as 2.8. In doing division, let's say 6.85 divided by 112. The initial answer is 0.0611388739. So you get the smaller number of significant figures. We have 6.85 is 3 versus 5 here. So you get the smaller number of significant figures and express the final answer in the same number of significant figures, 3. The initial answer has 2, 4, 6, 8, 9 significant figures. So to retain only 3, you drop numbers starting with 3 here. So what remains should be 611. The first 2 zeros are not significant. These 3 non-zero digits are significant, since the following digit to 1 is 3. You retain 1. So the final answer is 0.0611. So that's how you apply the rules in significant figures when doing calculations. Let's move on to scientific notation. Scientific notation is the convenient way of expressing extremely large or small numbers. For example, you have this extremely large number, 987,654,231. So this number is quite long. So to express this in a shorter manner, we use the scientific notation. How do you do that? For whole numbers, the decimal point is imaginary to the right of the last digit. So in this case, this is where you assume the decimal point. So to express this to scientific notation, to reduce the numbers, you move the decimal point to the left. 1, 2, 3, 4, 5, 6, 7, and 8. The base should have 1 non-zero digit followed by the decimal point and the rest of the significant figures. Let's say you are asked to leave 2 significant figures. So the first 2 digits will be left in the number. Since the next digit to the last remaining digit is 7, you have to increase 8 by 1. So that will be rounded off to 9. So that is rounded off to 9. So the Base should be 9.9, and then you use the power of 10. The exponent depends on the number of times you move the decimal point. So in this case, you moved it how many times? 8 times. So the exponent is 8. So that's how you express large numbers in scientific notation. For small numbers such as this, we have 0 point, or this is 6. We have tenths, hundredths, thousands, 10,000s, 100,000s, millions. So this is 10 millions. So the number is read as 610 million. So how do you express that in scientific notation? This is extremely small. This is way far from 1. So if in the first example, you move the decimal point to the left to obtain a non-zero, this time, you move the decimal point which is visible to the right. So you move that how many times? 3, 6. You have to obtain a non-zero before the decimal point. You are moving the decimal point up to after 6. So you will have the non-zero digit 6 followed by the decimal point that you moved. If you need to express the base or the number of significant figures in 2, then you have the freedom to add 0 to add significant digits or figure. So in this case, the only digit available is 6. If you are asked to express it into significant figures, just add 1. So the answer is, the expression is 6.0 times 10 raised to negative 7 is obtained because you move the decimal point 7 times to the right to obtain a non-zero. So that will give you an exponent of negative 7. Next, let's have the density. Density is a distinct property of all types of matter. Density is the ratio of mass to volume. This is the mass of an object divided by its volume. In equation, we have density equals mass divided by volume. So in symbols, we have D equals mass over volume. Its SI unit is kilogram per cubic meter. So these are some examples of densities of some substances. So as I said, density is a distinct characteristic of matter. It's one of the intrinsic physical properties. So for air, we have 0.001. The unit for these densities is gram per cubic centimeter. So ethanol, we have 0.79 gram per cubic centimeter. Water is 1.00 gram per cubic centimeters. And the rest follows. Let's have an example. Gold is a precious metal that is chemically unreactive and is usually used in jewelry. A piece of gold weighs 301 gram and has a volume of 15.6 cubic centimeter. So calculate the density of gold. So to determine the density of gold, we make use of the equation density equals mass over volume. We substitute the given mass is 301. So you substitute that here as the given mass divided by the given volume of 15.6. So that's 15.6 here is the denominator, cubic centimeter. So for the answer, you just divide the two and express the unit as the ratio gram per cubic centimeter. So we have the answer 19.6. Since this is division, let's take a look at the number of significant figures. This has 3 significant figures because 3 is between the non-zero versus 3 significant figures, all non-zero, so therefore significant. So you are not comparing different significant figures. So you express the final answer in the same significant figures 3. So 19.3 is the final answer, gram per cubic centimeter. So for this another example, a piece of platinum of metal with a density of 21.5 gram per cubic centimeter has a volume of 4.49 cubic centimeter. What is its mass? So for this, you can consider the equation density over volume, and then you derive mass. So for For the derivation, you cross-multiply density and volume to get the equation mass equals density times volume, and then you multiply you first substitute the given mass and substitute the given substitute the given density and volume, and then you multiply. You cancel the volume, so you will be left with the unit gram, and then express the final answer with the same number of significant figures that is smaller. So between the two, the smaller significant figures will be the basis for in expressing your final answer. So the final answer is given 6.5. Let's go to conversion. Conversion is the process of changing a unit of measurement from one form to another. For example, can you change 5 grams to gram? Yes. You cannot change 5 gram to a Newton, or 5 kilogram to meter. So if you are changing a unit, it has to be the same quantity. So if it's length, the unit you're changing it to should be another unit of length. So this is a unit of mass, you're changing it to another unit of mass. So kilogram can be changed to gram. Length, we have centimeter to meter, times second to millisecond. In doing conversion, we apply the most common technique called the dimensional analysis or factor label method. This is a procedure used to convert units in solving chemistry problems. So as a general equation, we have the given quantity. What do you do with the given quantity? You multiply that by a certain conversion factor, which is from an equivalent relationship between two quantities. So the product will give you the desired quantity. So there we have the given unit times the conversion factor. The given unit is in the numerator. You can have that cancel with the unit of the denominator of the conversion factor. So cancellation is always done between numerator of one factor and denominator of another factor in conversion. So that will make you arrive at the desired unit. Let's have an example. $1 is equal to 100 pennies. So how many pennies are equivalent to $2.46? So what is the given here? The given is $2.46. What is the given equivalent relationship? We have $1 is equal to 100 pennies. So the conversion factor will be derived from this equivalent. So that will give us two possible conversion factors. $1 over 100 pennies or 100 pennies over $1. So in doing the calculation, we start with the given. As we have seen in the previous slide, we start with the given. The given is $2.46. You multiply that by the conversion factor taken by the given equivalent relationship. You use the ratio 100 over 1 in order for you to cancel dollars. Numerator divided by denominator. So cancel dollar and you will be left with the desired unit. And then you do the operation 2.46 times 100. That will give you a product of 246 and copy the unit pennies. Another example. What is the equivalent of 57.8 meter to centimeter? The equivalent relationship given here is 100 centimeter equals 1 meter. But in this case, 1 centimeter is equal to 0.001 meter is the given. So from here, we can obtain two possible conversion factors. So you just use between the two possible conversion factors, that will enable you to do cancellation to arrive at the desired quantity. So for the solution, so this is what we're looking for. This is what we are given, 57.8 meter. Multiply that by the conversion factor taken from this equivalent. So you chose this because you can cancel meter here and meter in the denominator to arrive at the required unit, centimeter. So in doing the operation, you do division. 57.8 divided by 1 times 10 raised to negative 2, or simply 0.01. That will give you an initial answer of 5,780 centimeter. That in exponential, or in scientific notation, 5.78 times 10 raised to 3 centimeter. So that's how you do conversion. Let's do this. A person's average daily intake of glucose, a form of sugar, is 0.0833 pound. Pound is LB in symbol. What is this mass in milligrams? Given the equivalent 1 pound equals 453.6 grams. So to solve, you use the equation again, given times the conversion factor equals the desired quantity. So you start with the given, multiply that by the conversion factor taken from the given conversion factor or equivalent converted to conversion factor. You choose the conversion factor that will allow you to do the cancellation. So you cancel the similar units between numerator and denominator, and then you do the operation to arrive at the answer. So that's how you will convert the given to the required quantity in doing conversion. So that will be all for this topic. I hope you were able to refresh these topics in preparation for your next lessons in general chemistry. Thank you for watching. I hope to have you again on next videos for your general chemistry. So thank you.